Thank you very much, Helena, for the great introduction, and thank you everyone for tuning in. I think it's great to follow from Fabian talk, who introduced many of the challenges, especially with imaging data. So just like to reiterate, like I think imaging data is very versatile, so we can capture events at different scales, from the molecular level, the organelle structure, to the tissue level, so we can observe vascular networks or the tumors and the surrounding immune and stromal cells. And as well as like even at the organism level, we can observe the animal behavior. And this is all give us a great amount of information, but also great challenges for data visualization. And they also require us to think about flexible approaches, how we handle these data sets. So yeah, as I said, there is hierarchical structures, there is texture and intensity, and there is spatial information. So going back like to one of the challenges I'm working on, in addition to overlaying information on top of image, one of the things that I find like very challenging is we are able to generate hundreds and hundreds or even thousands and thousands of images very easily. And summarizing this data in an intuitive way that help us understand the biology is still a major challenge. So during my PhD, I was working to identify different phenotypes of breast cancer cell lines. And we have like different images that we can use image analysis to segment and identify different features like the length and the width of the cells, or the nucleus, the cell-to-cell adhesion, roughness, and protrusions. However, when I cluster this and look at the heat map, it's just give me the color, like the variable value as a color or bar chart, looking at the height of the bars, which is not very intuitive, and it's very difficult to relate back to the images. So something I was doing from time to time is to try to picture these, based on these numbers, how these different clusters look like. And as you can realize from this picture that I'm not really good at drawing, but also was wondering, wouldn't it be cool to have something that draw this for us? Like I give it the number and the software draw it for me. So there was nothing like that. So I needed to devise my own tools, and I got into BioVis then. So I developed a tool called Phenoplot, basically to represent, like to map data to structures, like an ellipse to represent the ellipse, the cell and its dimension, and another ellipse for the nucleus. We can fill the ellipse with symbols depending on protein abundance or mitochondria or the abundance of different organelles. To represent cell-to-cell adhesion, I overlay the border of the cell with a thick line, another half an ellipse to represent protrusions. The jagged border can represent the roughness and irregularity in the border. So just by using glyph-based visualization approach, combination of line styles, symbols, and colors, we can create very flexible picture of the data in multi-dimension, which should help us to better relate this data to the biology. And here is just the same data now, looking at heat map of different breast cancer cell lines. I can plot the average of each cluster using Phenoplot, and it's much more intuitive now. I can see straight away this cluster is small, while the second cluster is like have large cells that are roughly and have low cell-to-cell adhesion. On the other hand, the third cluster have less ruffles and more cell-to-cell adhesion. So it's just help us to understand how the cells look like and picture them, which is much more relatable to the original images and what we measured. So of course, this was the first version, and we just, in that time, I just defined a main ellipse and sub-ellipse and mapped the information and created very strict and rigid elements. And this is like not, it's very restrictive, and it was also on MATLAB, so we wanted to do something much more flexible. So now I took that to completely different level, where the user can map their data to any shape, and they even can draw their own shape and then map this information. What is even more powerful is when we start combining these different shapes, we can start creating complex structures that can then look like what we are measuring. So for example, at a cellular level, or even like if you want to represent the wall, well, and the wound in the center, or different cell types, all these things, you can create the structure in very flexible way. And to make it very easy and user-friendly, it is now available as a web app. So we use the JavaScript and Paper.js. So it's available at www.shapography.com. You can look at the examples and see also play with your data or some of the data available on the website. So how it works is basically once you create an object, you can map multiple numerical data you choose. It's very flexible and customizable. And this you can change the dimensions based on the variable value or overlay the object with a thick line or with symbols or fill the object with symbols depending on the variable value. You can change the color also depending on the variable, and there is another spike elements that also go around depending on the variable value. Other elements that we added is like the mesh. So this can also represent fiber structures like microtubules, or a grid to represent cellular density, or different compartments in the object or the biological system you are studying. So it's very versatile, and you can, for each object, map up to 10 variables. So it's very it gives you multiple dimensions. And how it works is we try to make it as simple as possible. So if you have your data in Excel, you can save as CSV file, you load your data, you add your objects from here, and then they will appear on the right, and you can name each object. And for each object, there is multiple elements that you can map the data, for example, the tumor size to the dimension of the object. And then you can, in very interactive way, see all the information in the website. So first example, very simple, 2 dimensions. We have wound healing data where we're looking how much the cells will close this created wound area under different conditions. And if you look at a bar chart, it's okay. You can see the differences probably and interpret them. But just to show you how this look like in Shapography, I created a square to represent the well and the cell density represented by the color hue, another square to represent the wound height, and we also can represent the density of the cells based on the mesh density. So plotting these numbers using Shapography, you can completely see a different picture. It's much more easier now. You see that these 2 genes have very similar wound area, but result in higher, like BLCG1 result in higher cell density versus AKT2. And this might give you information how these different aspects interacting with each other. Another example is from multiplexed imaging data. And here, like with multiplexed technology, we are able to capture 40, 60 proteins simultaneously in the same cells, either in culture or in tissues. So the challenge is these proteins have different localization, create different structures. So visualizing this is also a major challenge. And using the data from this paper from Lucas Pelkman's lab, there is HeLa cells for 40 proteins, and looking at UMAP will give you the overall structure in the data. So we can cluster that and identify that. Looking at a heat map, we can start interpreting the protein levels in these different clusters, but still it's not very intuitive and easy to relate to the images. So here I'm gonna show you how, step by step, how I created like a representation using Shapography. So here I created an object that looked like a HeLa cell, and then mapped the signaling of a certain protein to the periphery of this cell. To represent the context, I added a grid component to represent that, added another object to represent other signaling components at the periphery in the mTOR pathway, and then also represented the nuclear information like transcription factor level or the cellular proliferation based on a specific protein by filling the nucleus with symbols. Nuclear ball, which is also on the membrane of the nucleus, I represented it as simple filling on the border. Also added information for abundance of other organelles, filled the cytosol of the cell with the abundance of endosomes, which represented by this protein. So this is really give you a way to create structures, complex structure that at the end giving you a picture of how the cells look like. And here, like just positioning these glyphs in the dimensional space based on their UMAP position, it's give you a very nice way to interpret the clusters identified by UMAP. So you can see that these 3 clusters have higher cell density, while these have lower cell density. You can also see that signaling, how signaling is different in terms of mTOR by how much it's going around the periphery of the cell and so on. And of course, it's useful to still look at heat maps and UMaps. And this is another way just to help the biologists, especially, and people who are trying to interpret the data, to picture this in their head. Of course, as you use it more, you would be able to find it more intuitive to work with this tool, because it's quite new, and I appreciate it might be also a new way to think about things when you trying to plot your data using this. Another example is to represent the tissue microenvironment. Fabian talked a lot about this, and it is a major challenge. It is very complex. There is so many cell types, and how we can represent the interactions. So many questions we still interested to work on. But just like now, I'm trying to create a template for this. So representing the abundance of different cell types based on immune cells or tumor cells, and then also representing the signaling in the epithelial or tumor cells in a way like it might be more compact and more interpretable. So again, we can visualize this information. We can visualize the density of the surrounding tissue for different clusters to help us better understand the data, which is I think it's much more easier than to think about in terms of interpreting the data than heat maps. So in summary, basically, this is very versatile tool. What we're trying to do is to create different templates that suit different use cases. And this is very nice that you can, these different templates are saved as JSON file. So once we create the template, we can put it online for other people to use. And people can edit the template, like you don't need to use everything you see on, for example, in a specific template, or you can create your own and save it as JSON file and upload it again. And the website is the client side, everything on the client side. So you don't have to worry about uploading your data or anything. It all will be on your side. And if you have some interesting use cases, of course, we will be keen to learn and upload some examples on our website. So in summary, Shapography is an effective way to facilitate the interpretation of multi-dimensional phenotypic data. Of course, main thing is that you are not plotting the data on a bar chart. You are creating the way you want to represent your data. So there is some creative process, and then you can map this data, or you can use, of course, our templates. And what I find is also interesting that it might be an effective way to communicate information with wider audience, especially that looking sometimes at the images is overwhelming for people who are not very involved in imaging. So it can be another way to summarize the data. So yeah, that's basically, please try it and give us some feedback. We would love to hear from you, and thank you for listening, and happy to take questions.